Hey everybody, welcome to Om Learning Lab. Today we are going to look at one of the most famous problems in mathematics, a problem which has appeared across Olympiads, across examinations, and across quite a few puzzles as well. The problem is to find out which one is greater, e to the power pi or pi to the power e. Now there are quite a few reasons as to why I personally like this problem. The biggest reason being that someone who solves this problem the right way by following the right approach is going to learn a lot of things about the fundamentals of mathematics. And if someone is already familiar with all those things about mathematics, well, it acts as a really great revision problem. So, without any further ado, let's get into it. The first thing that comes to my mind when I see these two terms, e to the power pi and pi to the power e, is that we basically are dealing with just two numbers, e and pi, and there is some inequality over here, greater than, less than, equal to, something is happening. So for the time being, just for the sake of ease, let me represent that with a question mark. Now it's sort of a rule of thumb in mathematics, I can say, that whenever we are dealing with equations, we try to keep the LHS and the RHS, the left hand side and right hand side of the equations, having similar kinds of terms so that it's easier for simplifications. So for example, if we have an equation like, y square plus x is something like y cube plus x square, it just makes sense to take the x square terms to left and y square term to right, so that we have similar terms on one side. Following on a similar approach, which is quite intuitive to be honest, what I want to do here is bring terms of e on one side and pi on the other. The best way to do that is to raise both sides to 1 upon pi e. Now, please note that since both the numbers are positive and I'm raising them to a positive power, whatever sign was here, greater than, less than, or equal to, will not change. Just to drive that point home, if I have something like 2 is less than to 3, they basically have powers of 1, right? So I can raise both these sides to some positive power, let's say half. So square root of 2 is still less than square root of 3, so that's not an issue. However, I cannot raise them to negative powers. I cannot say 2 to the power minus 1 is less than 3 to the power minus 1. In fact, on the contrary, we know that half is more than one third. So this is wrong. But since both the sides are positive and we are raising them to positive powers, this is fine. The moment I do that, I end up with e to the power 1 by e and pi to the power 1 by pi. If I look at these two terms, e to the power 1 by e and pi to the power 1 by pi, it just looks similar in taste. It has a general form, the general form being very clear, which is something like something to the power 1 upon itself, x to the power 1 upon x. Now I can assign a variable y to this particular form, to this particular function, and then observe the behavior of this function at e and pi. Even better, instead of computing the value of the function at e and pi, can I just observe the nature of the function between e and pi? What I mean by that? What I mean by that is, if this is let's say this is a 2D coordinate plane, and this is my e is 2 point something, and this is my pi is 3.14, and this is my y. If I'm just able to find the nature of the function between e and pi, I don't even need to know the exact values. I just am bothered about the nature. So let's say the function was constant between e and pi. Then both these terms are equal and e to the power pi is same as pi to the power e. Let's say the function was decreasing. If it was decreasing, then e to the power 1 by e is more than pi to the power 1 by pi. Same goes for increasing. So we can just judge that by nature of the function. And of course, judging the nature of the function is actually much easier than actually computing the numerical value here. Why is it so? because in order to know the nature of the function, whether it is constant, increasing or decreasing in a given interval, we have to take its first derivative and observe whether it is positive or negative in that interval. Just a quick recap of why that is so. So whenever we talk about slope, so let's say this is a straight line, right? And I want to compute the slope of this straight line. So slope is computed as change in y upon change in x. Let's call this some del y. This is del x. So del y upon del x is my slope. This is how slope is defined, right? Now for any continuous function, like a general function need not be a straight line, right? It can be something like a random function, something like that. Now, if we want to compute the slope of that function at any given point, what we do is we draw a tangent. So for example, if I want to compute the slope at this point, what I'm going to do is I'll be drawing a tangent at this point, and then slope of this line will become my uh, it's basically the slope of the given function at that particular point, right? Now it's very easy to observe that for a function which is decreasing, the change in y will be negative. So I can drive that point home using this particular example itself. If I just observe this particular part of the function, right? Here my x is increasing, so del x will obviously be positive, x is increasing, but del y is negative, right? At this new point, let's say the slope del the y value is actually lesser than what it was previously, so del y is negative. Okay. So due to that, since slope is del y upon del x, change in y by change in x, slope is negative. So a function, if a function is constant, if I have a constant function, del y is 0, hence the derivative is 0. If a function is decreasing, then del y is negative, del x is positive, hence the derivative is negative. And if a function is increasing, both del y and del x are positive, hence we end up with a positive derivative. Keeping this in mind, which is a really fundamental concept in mathematics, we can solve this problem. So we just have to take the first derivative of this particular function and then observe it in between the interval e to pi. Now we will encounter another challenge. This function, this given function x to the power 1 by x, in order to take its derivative, we cannot take the derivative directly because we have the given variable, the independent variable in power. So how do we take the derivative then? Well, the standard way is we take log on both sides. So ln x is 1 by x, ln y, apologies, ln y is 1 by x ln x, taking log on both sides. Ln is basically log base e, for those who are wondering. And this is a very standard rule of log. If we have a to the power b, if we take log, it just becomes b log a. That's just how log works. Once I take log on both sides, I can then use differentiation rules. If I differentiate ln y, it gives me 1 by y, then derivative of y with x, chain rule. This is equal to differentiation. We'll have to use partial differentiation. 1 by x, derivative of ln x is 1 by x, plus ln x, derivative of 1 by x. It's same as x to the power minus 1. We can use nx to the power n minus 1. That gives me minus 1, this minus 1 multiplied with x to the power minus 2, which is basically minus 1 upon x squared. So finally I get the derivative of the given function dy upon dx as y multiplied with 1 upon x squared common, 1 minus ln x. This is the given slope. This is the required derivative of the function. Now, of course, we have to observe how it behaves between e to pi in order to make a judgment about whether the function is falling or increasing or constant between e to pi. Now, at e, it's easy to understand. Ln is basically log base e. So we have the property log a base a is basically 1. That's how it works, right? A to the power b equals to c, standard log property. I'm not going to elaborate upon that. So ln x at x equals to e becomes 1, so derivative is 0. But as x is more than e, what will happen to ln x? Log base ex, as x is more than e, this becomes more than 1. If this is more than 1, this derivative, if you look at x to the power 1 by x upon x square, this part of the top, between e to pi, I'm interested in e to pi, right? So I can just keep e as open for now, because at e it is 0. We know that the derivative is 0 at e. So dy dx, if I write it this way, dy dx at x equals to e is 0. Now, if I look at dy dx, the slope of the curve at x is more than e. This part will always be positive. X to the power 1 by x divided by x square. It will always be positive. But this part, 1 minus ln x, and ln x is more than 1, this becomes negative. So this is negative. That means between e to pi, at e derivative is 0. But between e to pi, definitely we are sure that this derivative is negative, or in other words, if the derivative is negative in a range, the function is falling, because derivative is negative means del y is negative, y value is decreasing. How it is decreasing, I am not sure. I can't judge how it is decreasing. So this option has to be correct. The function is falling. Now please note, I am not claiming that function is falling exactly this way, right? So function could fall in another way also. Let me elaborate just a little bit more on that. So between e to pi, I have found out that at e derivative was 0, but between e to pi, as x is more than e, the derivative is negative, the function is falling. But the function can fall in multiple ways. It can be straight fall, it can be a concave or upward fall, something like this, or it can be a concave downward fall. How it's falling, to know that we'll have to take a double derivative. We have to compute d square y upon dx square, but that's beyond the scope of this particular video. D square upon y upon dx square, apologies. So if we take that, the double derivative, we can definitely judge what is the nature of the function, how the function is decreasing. But that's beyond the scope of this problem. For this problem, to suffice the purpose of this problem, it's enough to know that the derivative is negative in the interval and the function is falling. Because since the function is falling, I can definitely say this is more than this. Value of the function at e is more than pi, or in other words, e to the power pi is more than pi to the power e. So this is how we can solve this problem. It goes through a set of fundamental concepts, not difficult, yet quite fundamental, which is we have to bring similar terms to one side, find a general function. Once we have general function, we need to know the concept that derivative of a function, if it is positive, the function is increasing in the interval. If it is constant, it's basically the function is constant, the derivative is 0. If the derivative is negative, it means the function is decreasing. And here is why, because derivative is del y by upon del x in the end. And then we take the derivative the right way by taking logs on both sides, and then we observe the nature of the derivative in the required interval, and finally we take the judgment call. That's all for today's video. Thank you for watching.